Oh, yes. This way you don't have to download, or you don't have to download the software itself. Okay, yours gonna be white, like brighter. If you want to change to the background like I do, you can go to tools, go all the way down to global options. Global option all the way to the last one, and then appearance. And then I choose solarized dark. If you want something else, you can do, okay, whichever. I like it darker, so it doesn't hurt my eyes that much. Someone, you want to turn off your mic so I don't bounce back? And then once you pick your favorite background, click apply, and then okay. We clear all that. All right, so the reason I'm doing this because later I'm going to use R. Maybe I'll mute you guys. I can mute you from here. If it's just me speaking and just make that sound. Oh no, somebody else. Okay. Well, you won't hear me. All right. Okay. So chapter 15. I'm not sharing my screen. Yes. I have your exam with me, graded. I forgot. Yes. Mhm. Yeah.
It says it's due Friday at night. Was it supposed to be Sunday at night?
No, I'm because Thursday you're gonna be time for the interval, and I don't want you to cram a lot unless you guys want to do it.
I don't know if you guys want to have to do Friday at night or Sunday.
Because there's interval. There's 16, chapter 16 as well. Huh?
Wait, when's chapter 16? When's chapter 16?
Well, chapter 16 gonna be finished on Thursday.
Oh, it's gonna be finished
So
Thursday.
2 chapters in 1 week. So I don't want you guys to cram. That's why I do that. It's only 20 questions.
So let's do 15 Sunday.
Okay, I'll how about Saturday for 15 and then Monday night for 16. Okay, all right. Whichever the book for as long as before the next lecture, I'm okay. Right. Yeah, during the break, let me show you something. I create all the slide. Yay! It's a lot of work. That's why I kind of procrastinate on your exam because I'm busy doing my slides. All right, chapter 15, sampling distribution. This is important. It's boring, but it's important. I'm sorry. It's not exciting. Later we'll be excited, but this is it's the backbone of everything while you do what we do. Like, people don't get statistics because they miss this. Like, why are we doing that? I don't understand. Because of this. So as long as you understand this chapter, it gets easier for you, okay? In terms of like understanding it. All right, chapter 15, sampling distribution. I don't know if you noticed, but for me, every spring I have this survey sent to my home asking about my income. Okay? Maybe your parents know about this. So the U.S. government's current population survey asked detailed question about income. The 100,028 household included in 2018 had a mean total money income of roughly 90,000. Can someone tell me what is the number 100,028 represent? What that number represent? What do you think? Is a population or sample size? Sample size, right? Sample size n. It's not population. And the $90,000. And this one? Sample, so X bar, right? For sample mean, right? It's sample mean. That's your X bar. Okay. So let me remind you what statistical inference means. Statistical inference means that we're going to use information from sample to infer things about population. Why do we do this? Because a lot of time we don't have money or manpower to get the data from population, right? For example, I want to know all the income of U.S. households. It's not impossible, but it just take a long time. Right? And not to mention people don't give back their little, they don't respond, right? So sometimes it's not accurate. So what I can do is I can choose a few thousand households and then average it out, and I can let's estimate. Now the question is, how good is my estimate? Right? That's all statistics is about. How good is your estimate? Right? If I do it one time, can I say that my estimate is good? Yeah, I'm nervous. Maybe it could be, but I'm a little nervous. I'm not sure. So what happened if we can do this many times? Right? What happened if we do this many times? Maybe we'll get a better result. So here is some definition about just terms wise. Population is everybody in the groups, right, that you want to know about. But a lot of times you don't have the access to. Sample is the subset of population. It is the smaller group part of population. So subset of population. Maybe I'll highlight. Subset of population. By the way, when I ask you guys is event is a subset of is a sample space. Most of you got it right. Some got it wrong. Population data are collected when all individuals in the population are measured, right, which is kind of difficult sometimes. If your population is large, like all US, like that range, it's kind of difficult, but we'll try, right? That's what we do census for. Sample data are collected from a subset of larger population. Now, parameter is the summary measure of population data. And then statistic is the summary measure of sample data. Can someone give me a parameter? You guys know about it. Can someone give me a parameter for population that you know about? You know, I know that you know it. You'll try. No, not number, a term. You said earlier. Yeah, the mu, right? That's parameter, right? So it's from population mean. And statistically, one of them you already know, which is X bar. I'm gonna denote population in red. And then sample in blue. Okay, population mean. It's parameter, right? Because it have the word population in it. By the way, sometimes I say true mean. I also mean population mean, right? Sometimes I say true mean. It's the same thing. It is parameter. Notation is mu. Sample mean is from the sample. It therefore is statistic, right? Notation is X bar. What about population standard deviation? Someone fill it out for me.
That's
First of all, is it parameter or statistic? Parameter. And notation? Yeah, very good. Thank you, sigma. Sample mean. I'm sorry, sample standard deviation. Is it statistic? Is it sample? And notation? Yeah, usually just S, right? Yes. Sometimes the notation is just S. But sometimes I write it in formula, I use SD. Remember S and P, so here's a little tip for you. Statistic come from sample, so SS, right? The parameters come from population, PP. It's easy to remember. We done this slide before, you can remember this a while ago. Okay, read this, and I want you to tell me the bolded number 3.8 and 160.2 are the parameter or statistic? You can put in the chat privately to me. All right, let's see. What was I? Okay, all right, Mohammed stat, Rami stat, Carly stat, Kai stat, Max, Tyler, Dan. Oh no, Daniel. Fatima, Melody, Rufisa, Fatima, Dave, Anthony, Maggie, Ella. Yep. Right. It is that. Why is it that? Why is it statistic? Why is it statistic?
because like this study. Oh,
11, right? Because it's come from the sample size of 11 subject. Sample data of 11 subject. Let's try number 2. Let's try number 2. How do I clear this? You know how I clear the chat? No, no, I cannot. Okay, only if I like log, if I leave and then come back, which I don't want to do. I'm sorry. For that. All right. Let's see. I don't know where it's again. We stop at Ella, right? Yeah, we stop at Ella. Okay. Medicine. Medicine. Say perimeter. All of them. Medicine. Where are you? Are you? Oh, yeah, that's you. Okay. Medicine. All of them. All the numbers. All 3 of them. Tyler, is it all 3 of them? Okay. Rami, Carly, Fatima, Ella. Ooh, good for you, Ella. Just wrong terms. That's all. I know what you mean. It's just the wrong terminology. Kella. Okay, I'm sorry, Kyle. Fatima, same. Then Daniel, Jessica, Maggie. Very good, Maggie. Very good. Yes, the first 2 is perimeter because it comes from where? It comes from the voter registration, right? So that's from the system. So if you vote, so it's going to be population, and then later on, what they do is they want to know the proportion of people who voted for a registered for Democrat or Republican. Then 34% down here. That will be your sample proportion. By the way, this is called sample proportion. You know how you have sample mean, right? And sample proportion. Proportion. We're gonna come back to this later when we do hypothesis testing for one population. And it's denote p hat. You don't have to know it now. I just kind of give you FYI. And the red part is called population proportion. And it's denote P. Again, just FYI. Okay. 15.2, we're gonna go a little bit deeper. We're gonna do some computation, just a little bit, not too much. Y is chemically delicate and must be carefully supervised and nurtured. Sulfur compounds such as dimethyl sulfide, short for DMS, are formed naturally in the process of making wine. DMS is present in all wines. At low level, it contributes to roundness, fruitiness, and complexity of wine. Unfortunately, at higher level, it can contribute to vegetative, cooked cabbage, onion-like, or sulfur smell. Winemaker need to know the odor threshold, the lowest concentration of DMS that the human nose can detect. That's why when you go to a restaurant, they kind of give you a sample. This is why it's good for you, so you don't smell that DMS level. People vary in their ability to detect DMS, and it's important to understand this variation. So our goal is to estimate the true mean, to estimate the population mean threshold mean in a population of all adults that taste wine or drink wine. Right? We don't know the true mean, but we're going to try to estimate it. So what we're going to do is we're going to present taster with wines that have different concentration of DMS. And here are the odor threshold for 10 randomly chosen people. So first of all, they want you to do the sample mean. How do I sample, bless you? How do I do the sample mean? It's no brainer here. What is that? Well, sample mean, X bar, Adam, yeah, right. So 28 plus 40 plus all the way to 17 plus 21 divided by 10. I'm not gonna do, I'm gonna use R. So you want to go do with me? You can. You have to. So mean. Oh, first of all, I need to put in the data. So y, I'm gonna call it y. You can call anything you want. I'll call it y. It's 28, comma 40, comma 28 again, comma 33, comma 20, comma 31, comma 29, comma 27, comma 17, comma 21. You can use calculators, it's not that bad. All right, I run it, control return or control enter or alt enter in not Mac. And then I want to know the mean of y. Right there, 27.4. So so 27.4. I didn't give you guys the unit, microgram something per liter. I think microgram. Yeah, micro right here, right here. Did I? Microgram. Oh yeah, microgram per liter. Okay. Now the question is that is X bar. What do you think X bar is the exactly right? Is the exact same thing as the population mean value? What do you think? Is this number 27.4? Is that your view? Huh? No, right, probably not, right? It'll be very, very unlikely. It could be sometime, but very unlikely that it's not. And I'm not even sure that it's a good estimate. I'm not even sure that number is good for the best for all population. Now, nonetheless, it is a reasonable estimate population view. Because one thing we can do is, if we keep taking larger and larger sample, the statistic X bar is guaranteed to get closer and closer to the parameter. Instead of putting sample size 10, I can increase to 50, 100, right? Then my X bar have a better chance to get closer and closer to the mean mu, population mean mu. So this sentence right here is very important, which is it implies the law of large number, which is we're gonna go next. Basically, the definition is the same thing as the same thing that I just highlighted in blue there. So law of large numbers say if you draw an observation at random from any population with a finite mean mu, which sometimes we don't know, as the number of observations draw increases, meaning increases the sample size, the measure of the observed value tends to get closer and closer to the mean mu of the population. This is why casino and the insurance company always win, right? As more people playing gambling and more people buying insurance, they always guarantee they get the profit back. They are backed by law of large numbers. All right, so this one right here, insurance. So you buy insurance when you face some risk that unlikely would maybe happen, right? So that's why you buy insurance for your house, for your car. You guys drive here? I noticed that unlike U of M or MSU, OU students tend to commute instead of stay on campus, which is nice. I do not stay in dorms. It's overrated. But maybe for some you guys are young, but it's expensive. All right. So what happened here? An insurance company look at the records for millions of apartment owners and see that the mean loss from apartment damage for each year, is it for each year? Yeah, for each year is have a average cost. The average cost is $150 per person. Now, what they want to do is the company plans to sell the renter insurance for $150 plus enough to cover its costs and profits. I want you to explain to me clearly why it would be unwise to sell only 10 policies versus thousands of policies. Why does it not make any sense if the insurance only sell 10 policies? Think of what does insurance do? Yeah.
Could it be like if they only sell 10 policies and like 2 of them actually hit, they have to cover it?
Yeah.
They lose more money as opposed to
Yeah.
like 20,000.
Right.
Same rate hit.
Mhm. Yeah, right. Because selling 10, sell only 10 policy. How much they get? 10 times 150, which is what? 1,500, right? Something happened if the unfortunate happened, whatever, house on fire, you total your car, God forbid, then it costs a lot to fix or to cover. Right? So as opposed to if you sell 1,000 of them, like 2,000, 3,000, costs a lot to fix. Maybe I'll say it costs a lot more than $1,500 to cover the damage. As opposed to selling thousands and thousands of policies. That's why they always gain. Because the more people drive, the more people buy insurance. Okay, so from the last 10 slides, the thing that I want you to get out of this last 10 slide, only one sentence. As sample size get larger and larger, what happened? What closer to what? X bar closer to mu, right? Sample mean closer to true mean. And then only to one sentence right now. This is important. This slide is important. I know it's all word, but you can understand what you're reading. I'll explain it to you sentence by sentence. So first, it says the value of statistic from a random sample will vary from sample to sample. Does that make sense? To you? You think that makes sense? Can someone tell me why does it make sense? What random? Explain more. Maybe you kind of get the blurred picture, but try to put it in exact words. Why does it make sense? Therefore your X bar will be different, right? Yeah. So for example, if I want to know what's your average score, my exam right now, right? So I average you out, and then another professor do the same thing for his class. It will be different. So my X bar different than his, and different than somebody else want to do their class. So the value of statistic is so this sentence right here say. This sentence right here means X bar is a random variable. what random variable means it changes. It changes depending on the sample size that you pick. Right? Of course, it's assumed that it's simple random sample. It's non-biased, but it will be fixed and X bar will be different. The second sentence say, the statistic is a random variable, which just it will have a probability distribution. What does that mean? That means if I have a bunch of X bar, what if you have data points, what do you do? First thing you do, if you have a data point, the first thing you do is, what would you do? Say you assess session, what would you do? The first thing you do is, oh, okay, and then what else? How do you do that? No, I won't be able to tell. How do you know that there's an outlier or not? You eyeball it, right? You eyeball what? Huh? The graph, right? The graph. You grab it. Once you have a data point, you grab the first thing you do, you grab it. I want to know what the shape is, right? Is it normal, uniform, or something else? Right? So when I have my bunch of X bars, say my class, and then other professors, so I have X bar 1 here. I'll use green or blue. Maybe my X bar 1 is right here. Other professor X bar 2 is right here. That's his average exam score for his class. Other professor right here, right? Well, and then right here, and then other people, a bunch of people, right? And then I'm gonna graph it, see what happened, right? See what happened. And I'm gonna say this, spoiler alert. If I increase my number of repetition, if I do a lot of X bar, a bunch of X bar, a lot of them, and also increasing my sample size, instead of 10, I have 100. Then over time, when I plot the bunch of X bar, I'm gonna see a normal distribution. Again, this is spoiler alert. It's not on the slide, but information ahead. So the probability distribution is called a sampling distribution. Sampling distribution is basically a bunch of X bar on the X-axis. That's all. Okay, don't think too hard. When I say sampling distribution, you imagine the picture, you graph a bunch of X bar on the X-axis to see what shape it has. That's it. And why do we do this? Because we want to know what is the probability distribution. Remember, you guys remember this? This is my Y-axis. Sometimes it's called frequency, right? And then I can ask you what I can ask you, and then I can ask you about the X values, and you can tell me what is the probability the X value covered. Right? That's all it is. All right, so here is the next slide is basically exactly same thing I say. It's just back to the example of the Y over threshold. What they have is they repeat this process every time they take out 10 people, and they do it 1,000 times. And once they have 1,000 X bars, they put on the X-axis and they see what kind of distribution it has. In this case, it has the distribution of the histogram, right? And then this little curve right here, what is called? Remember what the curve called? No. It's a bell curve. But what's the curve called? Density curve. Smooth out density curve. Of course, your data is gonna have a look of a histogram, but what we do, that's what people do, is they smooth out. It's easier for the picture, so I don't have to draw a bunch of bins. That's exactly saying what I said. So maybe I'll do something here. So a bunch of also size 10. And this process is you do it 1,000 times. Once you have those, just to plot the X bars on the x-axis, and what happened is they see this shape, which is the good news. We want to see normal shape. Why we want normal shape? Because we have formula for normality, right? The Z-score. Let's shoot. Okay. All right. So sampling distribution is a statistic. Let me. It just repeated what the other slide said. Maybe I should put it here. So sampling distribution is a statistic in this case. What's your statistic in this case? What is your statistic? What is your statistic? X bar, right? Your X bar. It's the distribution of value taken by the statistic in all possible samples. How many you have time to do 100,000 of the same size from the same population. Make sure you don't pick the same people. As long as you don't pick the same people. Population distribution. Oh, by the way, and this one is the random variable. As opposed to population distribution. Let me ask you a question. You see if you can answer. Do you think population distribution is a fixed values or random values? Just use your common sense. Is it a fixed value or something that can jump, like changing? I'm talking about just one population, just one particular population.
In one sample, I feel like the distribution usually stays around the same, and then it
Say
starts
again,
to change.
speaking?
Mohammed,
What'd you say, Muhammad?
I'm saying in one specific sample, I feel like distribution, population distribution would remain fairly constant, but then it changes when you bring differing samples.
Good, very good, right? Yeah, I think I got what you said. So Muhammad said population is the fixed values, what he meant. Why is it fixed? Well, you only have one mu, right? Which is you try to estimate. You only have one sigma, right? Distribution. Maybe I should say population parameter. Population parameter is a fixed value. In this case, your mu is fixed. Only have one mu. That mu is important. Sometimes, a lot of time we don't know. That's why we use X bar to estimate. Think mu or sigma or what is sigma square? Do you guys remember what sigma square? What's S square? Yeah, variance. You can have a negative standard deviation, but you cannot have a negative variance. Why? You square it. You square everything, it will turn positive. Let's do, let me see. Maybe we do one more and then we'll take a little break. We'll take a break and then I take your attendance and then I'll talk about the syllabus. I changed it a little bit. Okay, sampling distribution versus population distribution. It's from your book. I think it's from your homework. Forgive me if I do your homework. Show you. Excited to do it. Okay. American 2018 American Time Use Survey contained data on how many minutes of sleep per night each of 9,600 survey participants estimated they get. The time followed the normal distribution with mean 529.2 minutes and a standard deviation of 135.6 minutes. Let me highlight something. As soon as I read, I know my, oh, by the way, the first sentence is a population or sample, but 9,600 survey participants. from, no, the population start out at 9,600 people, right? So it's going to be your population. So let me highlight in red, like I said, population in red. So all the cents and years, they all population. And the nice thing about my population is follow a normal distribution, which is nice. If it doesn't say anything, you stop. You cannot do anything. You don't know the distribution. Is it uniform, normal? As a simple random sample of 100 participants, now is going to be sample, right? Simple random sample, 100. So this is my N. Of the participant has mean times X bar, 114.4 minutes. And the second simple random sample, same size, have a mean of 539.3 minutes. I don't know why they give you this number because we don't use it. As many simple random samples, the many day of the sample mean X bar follow a normal distribution with mean 529 point, by the way, this should be 0.2, my bad. 0.2 minutes and a standard deviation of 13.56 minutes. I'll explain it to you why they have that. I highlight this again. I don't need this because I don't use this. Okay, so the one I highlight in blue is a this what follow what the sample mean X, my sample mean X bar follow the little wiggly thing mean follow a normal distribution N with mean 529.2. 529.2 is the same thing as the mu, right? And let me, and 13.56. Where does that come from? Where's that come from? My population standard deviation is 135.6. I lose 10 units. Well, it's come from this formula because you are no longer on population, you on X bar now. So X bar have the same mean, the means does not change, but the standard deviation change. It changed by this formula, sigma divided by square root of n. And I don't have enough space to write. So let me write it here. I need to charge my thing. Let me charge it now. And you should remember this formula is very important. When you repeat it, keep doing your sampling. That's what happens. Okay, what is the population? We say that the population is 9,600. And what value the population distribution describe? Well, 9,600, that's a value. So 9,600 survey participants from 2018 American Time Use Survey. You're gonna say all out. Yeah. Context. What is the distribution? I already answered it to you. Just summarize it for me. What is the distribution of my population? Can someone tell me my the population distribution? I said it to you earlier. highlight it for you too. What the name of the distribution first? Normal, right? And then mu comma sigma, right? Which is n mu is 529.2, sigma is 135.6. Oh, because that's the this the distribution of a sample mean. The distribution of sample mean is have the same mean. Remember what we say? As sample size get bigger and bigger, x bar get closer and closer to mu, right? So we don't change the mu. We're not gonna say x bar here. Sample size large. But the standard deviation change. It changed by what? It changed by the sample size. As sample size get bigger, what fraction gets smaller or bigger? Smaller, right? Sample size big, which is a good thing. Small standard deviation. So X bar follow this distribution, but this is the population distribution. This is sampling distribution. Maybe I should have given you one more slide. And here, I'll hang on, yeah, right here. How about this? I'll put it right here so you don't forget. Better? Oh, by the way, it's only true if what? The red part only true if the problem say is the follow normal distribution, okay? If it doesn't say, then you cannot assume. Like you did on the exam. A lot of people assume they're independent.
So you said, which one?
Assume the problem says the population follow normal curve. The blue one is a bit more complicated. I'll tell you later. That's later. The blue one, maybe I'll tell you now. The blue one, if the population is normal, then the blue one is automatically normal. What if the population is not normal to begin with? Then we have another rule called the central limit theorem. It's a very powerful theorem, if you ask me. The most powerful, I think one of the most powerful theorem in statistics. But I'm going to talk about later. Okay, I'll talk about later. But let me finish answering these questions so you can take a break. What a value does sampling distribution X bar describe? Or X bar describe? What does it describe? It describes that simple random sample of 100 participants, right? The number of hours sleep per night of 100 participants. And what is the distribution of a sampling distribution? I give it to you there, right? What is that? Is n mu does not change. Mu does not depend on sample size, but the standard deviation does. And standard deviation now is a sigma divided by square root of n. On the exam, I will give you mu and I will give you sigma. And n too. So in this case, if you what? Yeah. So mu is 529.2, and then sigma is 135.6. Is that right? divided by square root of 100. Well, square root of 100 is 10. That's equal 10. So it's equal to 135. I'm sorry, 13.56. That's where it comes from. That's what they tell you in the highlighted blue. All right, let's take a break here. I'll take your attendance. Rami.
Yeah.
Let me interrupt you a little bit, and then I'll let you get back to the chit chat. Okay, so syllabus, I changed a few things. Well, the exam days I never change, but I changed the chapter around. So chapter 15 originally, it's gonna take me 2 lectures. That's too long, consider how boring it is. So I'm gonna try to finish as much as chapter 15 today, and then maybe the first 20 minutes on Thursday we'll finish chapter 15, and then finish chapter 16. Chapter 16 only like 17 slides, so I think we'll be okay. Chapter 17, same thing. It used to be 2 lectures, but that's because other professor doesn't have a slide, have to write a lot. That's why. But my slide, all you have to do is to read a bunch of definition. That's all. Chapter 20 and 22 is important. So I spread it out into 2 lectures each. Now, bad news, sorry, it's a lot for exam 3. Remember, because you guys say what? You don't want chapter 14 on your exam 2. So, you have a question? Yes. I'll tell you, I'll send out email. But it's gonna be all slides, okay? Or even homework. Okay, so the bad news is that you have a lot to cover for exam 3. See how many chapters? Chapter 14, 1, 2, 3, 4, 5, 6, 7, including 18. What I'm gonna do is, it's gonna be 8 questions. 1 question each chapter. Is that fair? So 8 questions. I think that's fair.
2 extra credit.
Maybe I'll include. No, you don't. I'm not including extra credit because I already did.
Yeah.
Because I'm gonna send you guys a extra credit project. Remember?
Yeah.
That's worth what? From 20 to 30 points. So what is that? Okay. Yeah, R30, and then Google Sheet is, or calculator, but the Google Sheet is 20.
The exam is really close to the first day of Ramadan, so like there's so if we got like maybe like an extra 10 points, or there's like a celebration.
And I'm very generous. And there's one more extra credit, which is what? You tell me how you feel about stat class, which is worth up to 5 points. If you can make me laugh or you sing, that's definitely 5 points. I'll show you something from my student from U of M. They sing for me. I'm like, wow, and she's so cute. She sing for me. I had her permission to share, so I can share. I asked her like, can I share for my other class, a different like university? She's like, that's okay. So let me tell you what happened to the second extra credit opportunity. It's very easy. Please don't write letter. I don't like reading long stuff. But if a very good letter, then go ahead. But usually I don't like letter. Yeah, by either you sing for me, or you can make a poem, a funny poem, or a joke, like a cartoon, I'll show you what I meant. Oh no, stat has to be stat. Stat. Well, I mean, up to 5 points. If I really enjoy it, it'll be 5 points. Yeah, if it's like, okay, mediocre. All right. Here's one student Q. Confident interval. This is what kind of rule is this? Empirical rule, right? And he put his face on it. That's kind of cute. Oh yeah, you can draw. You can make jokes.
Okay, perfect.
Yeah. Here, very simple. I prefer these instead of like long letters. It's like Putin with his nuclear buttons. Outliers. Come on, let's take it a little slow. Oh God, it's so slow. Never mind. Let me see if I can do this one. Okay. Oh, sorry.
Surveys are great in so many ways.
She's so
They
cute.
can
She's so cute.
gather wide ranges of
I'm not gonna make you
data,
listen to the whole thing,
but there's room.
you can do in group too. Let me show you one of the students did in group. What? No, it's just you gotta want to do it together. Some people want to do it together. Remember somewhere here. Somebody share for me. It was in my class. It was somebody else's class at U of M. And share for me. Huh? Oh, our Studio Cloud is so that you don't have to download anything. Just sign in and then. Yeah. But if you already have it on your computer, then it's fine. Some people say they cannot download for some reason. I don't know why. All right, here. Let's see. Hang on. It was just making a TikTok video. So you can do that if you want. Montana. But you can do that, like 4 people. You think I can do it? No more than 4. It's too much. Well, I mean, I'm the only those little girl did, so they get credit, but the class doesn't get the credit. So yeah, something like that. You can write. I don't. So here's the letter. Dear Uncle Joe. It's just he talked about the New York Knicks. How statistics work in the game, the sport industry. Important to have, yeah. So it's long, but I like it. So it is a good paragraph, but a lot of time I don't like it. Too long. I don't like to read.
Okay, great. But like, we have to read.
You can write you like. Okay, let's get back to our things. Where are we? All right, so far, as sample size get bigger, X bar get closer and closer to mu, which is a good thing. And then the second thing is what? Is sampling distribution follow a normal distribution of the same mu, but the standard deviation becomes what? Sigma divided by square root of n now, right? So those are 2 things you remember now. Okay, so what we've been talking about how we use X bar to estimate mu. So this the arrow mean estimate. This letter E, estimate mu. For when I talk about mean, when you mean, you measure things in quantitative variable. Okay. For example, height, weight, distance. Why? Because I can average you guys height or average you guys weight or your exam score, right? But remember the exam, the last exam number, I forgot what number that is. It's like parental satisfaction. A lot of you ask me is if you assign number to your level of satisfaction, like from 1 to 5, 5 being very satisfied, 1 being least satisfied, then it become a quantitative. Oh, I'm sorry, become a quantitative. Why is it wrong?
Because it's still associated.
Yeah, it's still it's nature. It's the categorical, right? You have to assign number to do the things, as opposed to like your weight, your height. Like originally, you can just compute in and get the X bar. Same thing with jersey number. Can I average jersey number? Say a hockey team. No, you can average it, but it doesn't have any meaningful. It doesn't mean anything. So even if there's no number, it is categorical. All right, so this problem, how many hours per week do you work? Do you guys work? Raise your hand if you work part-time, full-time. Good for you. Very good. How many hours per week do you work? A poll was conducted by a Center for Workforce Development, a probability sample of 100 full-time workers in the United States. Resulted in a mean number of work per week, hour per week is 40 hours per week. Can you tell me what's the population here? I just wanted to close. What is the population here? Doesn't have to be a number. Very good, very good. All worker. I like it. I got when you say all worker in United States, all worker in USA. And then parameter that we're trying to compute. Well, you only know one. The mu, right? The mu, which is the mu is the inverse is, and in context. Population. Maybe I'll say average. You can say mean average. Average work hours. It just sounds nicer. Average work hours per week of all. Oh, by the way, full-time worker. Forgot about that. I only care about full-time. We don't care about part-time. Full-time worker. Full-time worker in US. What's your sample? Very good. Oh, sorry. Medicine, right? Thank you, medicine. 100 full-time workers. And then statistics. The X bar, which is, yeah. What X bar equal? This is sample mean, sample average. You can say sample mean, sample average. Work hours per week of 100 full-time worker, right? You select It's a good problem for a quiz. Maybe I'll give you a problem like this. I'll ask you, you pick, I'll have a drop down menu for you and you pick. Mm-hmm. For both chapters, 15 and 16. I hope you guys watch a video for about chapter 14. Okay, good. Because what we're about to do is kind of related to chapter 14. Now, question. So these are just open-ended questions. You won't be able to answer them all. But can anyone say how close is observed sample mean X bar of 43 is to the population mean mu? Can you say that it's a very good approximation? No, right? No, absolutely not. Can't. No, not right now. No, not right now. I hope it's a good estimate, but keep my finger crossed, but I don't know. Right? I'm still nervous. If we were to take another random sample of the same size, would you get the same value for the sample mean? What do you think? Very unlikely, right? Maybe sometimes it's happened, but I would say very unlikely. If all the sample means are the same, when you put it on the x-axis, what kind of distribution are you gonna see? Instead of normal, like up and down, what do you see? You see uniform, right? Same, no variance. So the last question is, we can't answer it now, but we can answer it when we finish the central limit theorem. What are the possible values for sample mean X bar if we took many random samples of the same type from the population? Well, I don't know. Okay. But what I know is what would the distribution of possible X bar values look like? What can you say about distribution? Okay. All right. So, but what can you say about the sampling distribution of X bar? Basically, what can you say about the distribution of X bar? Is what? X bar follow what? A normal, good. Is mu good? Mu does not depend on sample mean. I'm sorry, sample size. Remember that. It's a good question. But standard division does, right? So standard deviation is sigma divided by square root of n. Now, maybe I'll say it right now, and then later when I repeat it, maybe you remember it. It's only happen, X bar only follow a normal distribution in certain conditions. The first condition is what? If the population, what? Population, I say it wrong. Population has a normal distribution. If the population have normal distribution, then this is true. Great, nothing wrong with that. What if the population is not normal? Michigan is not normal. Well, then we have a backup, and that's called the CLT, the central limit theorem, which we're going to talk about later. Okay, so what happened? The population is not normal. Well, we'll see. We'll see what it says. But before we do that, I need to say something about unbiased estimator. An unbiased estimator is a statistic, in this case, X bar, used to estimate a parameter where the mean of a specific sampling distribution equal to the true values. So let me highlight something. I'm gonna translate word by word. Can someone tell me what's the statistic here? X bar, right? X bar. That's the right now. That's the only one you know. Well, you know S, but we don't talk about S. Is estimate what? Estimate. You estimate the parameter, which is mu. Now, where the mean of statistic sampling distribution, let me highlight something here too, maybe in yellow. This is important. While statistic is X bar, and the mean, maybe I'll go up here. Maybe I'll go up here. And the mean of X bar, we denote E of X. Remember the expected value? Do you guys remember in your first exam, I kind of make you do this, which you don't understand why, but I never say you why. E of X equal mu equal whatever you want to do. Remember that? Well, that's the reason why now, right? Because it's an unbiased estimator. So E of X bar, so the expected value of X bar is equal right here, equal to the true values. I'll keep up with my color. The true value mu. Then X bar is an unbiased estimator of mu. There's a proof, mathematical proof for this. You are not responsible for this level. It's not hard, but I'll save you some headache. You don't have to worry about this. Maybe if you take more statistics class, they may you do it, but not this level. I guess right now you take my word for it. It's an unbiased estimator. So if you can prove that E of X bar equal mu, then X bar is an unbiased estimator. Okay, this slide right here is wrap it up what I said up here. So you guys fill in the space for me. So mu, we know the population mean, X bar sample mean. If all possible random sample of the same size n are taken and X bar is computed for each, then the average of all the possible sample mean values is equal to what? Is the summarize of this slide. Average of all possible sample mean. Average, you know, E of something. X sample mean X bar, right? E of X bar equal to what? Mu, right? Population mean mu. That's why you can understand the question before you actually answer. Population mean mu. Thus, the sample mean is unbiased. If you can prove E of X bar equal to mu, then you conclude is the unbiased estimator of mu. Well, X bar is the unbiased estimator of mu. And the standard deviation is given by this formula. I already told you about this. So it's nothing new there. Right here. This one right here is what we cannot fill in this part if the population distribution is not normal. If the parent or your population has a normal distribution, then the distribution of the X bar is normal. Nothing new there, right? But what if the parent population is not necessarily normal, but the sample size is large? How large is large enough? I'll let you know. Then the distribution of the possible sample value of X bar is approximately normal. So this is a very powerful statement, right? Even though I don't have a normal distribution to begin with, but as long as my sample size is large, maybe I'll tell you now, is as long as sample size is at least 25. At least 25. Then I can say that my X bar is follow a normal distribution. And that's called a central limit theorem. You don't want to see the proof of this? Matter of fact, you're not going to see this until grad school if you ever go to stat major central limit theorem. So I don't want to bother to show you. The other proof, the unbiased proof, is easy. I'm sure if I show you, you can get it, but not central limit theorem. It's require a lot more. Okay, right here. So here is the central limit theorem. And x follow any distribution, any at all, uniform, less mu, right, I don't care. Right? With the mean mu given and the standard deviation sigma is given. I forgot the space there. And n is large. How large? Yeah, at least 25, right? Then x bar is approximately normal. That, right? Did I go? No, I didn't go over. I really hope that we can finish a lot today. Do you have any questions so far? I say I talk a lot during this lecture. I told you it's kind of boring. It's a lot of theory, but as I need you to get this in order to move on. Otherwise, you can do it. It's just kind of blurry. SRT test score, a particular test for measuring various aspects of verbal memory is known as the selective reminding test, SRT test. It is based on hearing, recalling, and learning 12 words presented in a client scores for various aspects of verbal memory are combined to give an overall score. Let X represent overall score for 20 years old. Such score are normally distributed. Yay! What I hear is great. It's good news, right? If I don't have normally distributed, I have to rely on what? My sample size. Right? But I heard normal distributed, so I feel kind of relieved. With a mean of 126 points and a standard deviation of 10 points. And because it's normal, I'm allowed to draw a normal curve. Can someone tell me the distribution on top here? Right here. Yeah, thank you. 10. So you should know by now. You did this on your first exam. What do I want? I want to know what the probability that a random selected 20 years old will have a score above 134. Maybe I'll say 134 right here. It's above, so should I shade right or shade left? Right. So I want to know this little area right here. I want to know what is x is greater than 134. If you do equal, then it's fine. 2 greater equal 2 doesn't matter to me. Do you guys remember how to do this? What do I? Z, right? X minus mu divided by sigma. X is 134. That's your observed value. Right? Mu is 126. Divide sigma is 10. What you got? Is it 0.8 or something? Huh? Okay, thank you. 0.8. What do you do next? You look it up on the table, but what the table give you? Which one? The left? Or, yeah, it gives you the left, right? It gives you the left. That's why it's a lot. It's something is a point something. It's like 90-something percent. Well, at least 80% something. But you want this probability, so what do you do? Yeah, maybe I'll use, hang on, maybe I'll use, can you guys see yellow or no? Yeah, I can. Maybe dark green? Okay, so, oops, I want dark green. I wish I can add more colors. So I don't have to keep going to the circle thing. So, so this right here, this value right here, it gives me P of X is less than 134, but I want it greater than, right? So what do we do? Complement, right? Want to subtract something. I don't know what it is. So I'm not gonna do by hand. I'm being lazy, so I'm gonna use R. Oh my God. Maybe it's lower. But come on. There we go. Erase that. All right, P norm. That's your command. X, so it's 134. Your mean is is it 126? Standard deviation is, oh, I'm sorry. I have to say mean, otherwise I won't understand. Mean 126, and then SD is 10, and then lower tail. What do you think? Should I say false or it's true? False, right? You don't want right tail. You don't want lower tail. False. Can't see. Right there. Roughly 21%, which is makes sense, right? Which is makes sense. If you have like 80%, then you know you have to subtract one because that tiny little area should not be 80%. So I'm gonna, so I say I use minus 0.778 something. And then it should give you 0.211 something. And that's your answer. Do you have any questions? This is old stuff. Number 2, a random sample of 9 20 years old will be selected. So the sample size here will be what? N equal, I'm sorry, I said I use blue for sample size, but I'm running out of color, so I'm gonna use red. Maybe I'll use black. 9 is your sample size, right? Now it's only 10. 9 is only 10. What is the probability that all 9 will score 134? Your sample size is small. But it's normal, population is normal anyway, so we're okay. I want to know P of, oh, maybe I'll use red. I want to know P of all 9. All 9 is below 134. What is the probability of one random selected person is below 134? Yeah, right. One randomly selected person that below 134 is equal to, you know what, I should have said P of 0.788 or on here. We can do I don't, I got used to the MacBook. Right there. You do true, we're gonna give you a left tail. Now, because, do you agree with me that all 9 people who take an exam or the test, whatever test that is, they are independent of one another? Like you, right? Assume you don't got to talk to each other, which I'm not allowed to. So you independent. If independent, what kind of rule do we use? Multiplication, right? So 0.788 times 0.788 times 0.788, 9 times, right? Or raised to the 9. you can use your calculator in this. Oh crap. I messed it up. No, I didn't. Eh. 0.12. 0.1, maybe around to 4 decimal point 1173. Do you guys have any questions so far? This is from chapter 14. A random sample of 920 years old will be selected. What is the probability that the sample mean score will be above 134? Now, they ask different things now. Want to know P of X bar is above 134. In order to calculate this, we need something. We need what? Remember, in order to calculate this, we need what? Remember, it's normal. Remember, it's normal. So almost done. Just bear with me for a little bit more. But because it's X bar, what should I? Mu doesn't change, but what should change? The part of the denominator, instead of sigma, it's going to be sigma what? Yeah, divided by square root of n. Okay. Plug it in. So what's sigma divided by square root of n? Yeah, I'll use black for now. So x is 134 minus mu 126 divided by sigma divided 10 divided by square root of n, 10/3. And you can look up table, right? On the exam, I want you to show me all the work, but right now, I need we kind of close to the time. So I'm gonna use R. Okay, so same x, same mean, but standard deviation it changed. You want the lower tail, or you want the upper tail? Look at the problem. Don't look at me. We want lower tail, upper tail. Upper, so false, right? Right there. Very small. I wish that the button I can just press and then just go back to my laptop. I mean my tablet. Some number, I don't know, some number. And then what you're gonna do is you're gonna look it up, right? So P of, well, we use R, so this point, forgot what was that was, 0.0081. Let me ask you a question. Are you comfortable with me not showing you all the work here? Is that okay? Can you do the rest? Because I gotta use R to get the probability. You can do the rest, right? Okay. It's the same thing as problem 1. It's 1 minus something. something like this on the exam.
Also done for the probability that someone gets above the 134 and then just breaks that.
No, they don't ask about that. They ask about X bar. The other one is X. Example mean score. Yeah, on the exam, make sure you read the problem carefully. What's the difference between 2 and 3? 2 is just the regular score, right, for each individual. Here is the average score of all 9. Which is makes sense. Do you think number 3, you have this tiny probability? Do you think it makes sense? Just like all of you get 90% of my class, probably should be small. Oh, small. So it makes sense. Let me see how long do we have. Yay, we're almost done. Maybe should we do this one? No, we'll save this one for next time. So because 5 or 3 minutes, it won't be able to. All right, we're gonna stop it right here. Next time I'll continue for about 20 minutes and we'll be done. And I'll change the homework date